Welcome back to the Algebra 1 series. Today we are up to section 1.4, the distributive property of multiplication over addition. So what does that mean? For any numbers a, b, and c, when you multiply a times the quantity b plus c, the a is distributed to the b and the c. So a times b plus c equals a times b plus a times c. Now, this second line here is a different way of writing the exact same thing. And typically you don't see it written this way, but when you multiply two things together, it doesn't matter what order you multiply them. So b plus c as a quantity times a will give you the exact same thing. The a is distributed to everything inside of the parentheses. So we're going to do an example with numbers. If we were doing this in a, we'll say, normal way, we would just add the 3 plus 5 to get 8, multiply the 2 to get 16. So we know that this equation equals 16. But let's use this distribution method to show how this works. So in this case, 2 is what's being distributed to the items inside of the parentheses. So it'd be 2 times 3 plus 2 times 5. 2 is a in this case, being distributed. So I'm just going to regroup those with some parentheses. 2 times 3 is 6, and 2 times 5 is 10, which gives us 16, so it works. It's the same number. So, taking the next step, we're going to throw in some variables. The exact same process is followed. In this case, the a, or the thing being distributed, is the 3. So 3 times the quantity of x plus 2 equals 3 times x plus 3 times 2. And it simplifies to 3x plus 6. There's nothing more that can be done at this point. This is as simplified as the equation gets. Something to keep in note is that it doesn't matter how many items are within the parentheses, you would distribute the outside variable to every single entity. This is also true for subtraction. The sign follows along as you distribute through the parentheses. So here's an example that's got a plus and minus and more than two things inside the parentheses. 6 times the quantity, s plus t minus 2w. So we're going to distribute the 6 across the things inside the parentheses. So 6 times s plus 6 times t minus 6 times 2w. And it simplifies to this. There's nothing more that can be done with this equation. We just distributed the 6 across the items within the parentheses. So let's jump over to the whiteboard and do some distributive examples. Okay, we're here at the whiteboard. Let's do some distributive property examples. Let's start with 2 times the quantity b plus 5. So we have to distribute the 2 to all of the items inside the parentheses. So this would be equal to 2b, 2 times b, plus 2 times 5, which is 10. And that's it. There's nothing more that can be done with this problem. Let's go to the next step and add some more guys inside of the example here. 7 times, say, x plus 4 plus 5y. So 7 needs to be distributed to everything inside the parentheses. So this would be equal to 7 times x plus 7 times 4, which is 28, plus 7 times 5y. So you can multiply the 7 times the 5 times the y, which gives you 35y. So let's look at one more example. We'll do this over here. We'll say 4 times 3 minus 2x plus 3y, which Just want to focus on the signs here. And these are the kind of things that will trip people up. Positive signs, negative signs, carrying signs. So 4 times 3, well, that's easy. That's equal to 12. Now 4, 2, and x. 4 times 2 is 8. This is a negative sign. So negative 8x plus 4 times 3 times y, 12y. Okay, let's jump back to the slides. So the next topic we're going to cover is factoring. So if the statement of the distributive property is reversed, this is called factoring. So this is that forward backwards idea. We just distributed. Factoring is the reverse of that operation. So if you have an expression that's AB plus AC, you can factor out the A. You can pull it out and be left with A times B plus C. So in this case, A is the common factor that is pulled out of the equation. So here's some examples. Again, we'll keep this up top. AB plus AC equals A times B plus C. So in this statement, 3x plus 3y, 3 is the common factor between those two things. So we are going to factor it out. So it's 3 times x plus y. As you can see, this is just the opposite order of what we did in the first half of the video. So we'll take the next step. We'll make it a little more complicated. 7y plus 14 plus 21z. So what is the common factor between those three items? In this case, it's 7. So you can pull a 7 out of each of those things. So 7 times y plus 2 times 7 times y plus 3 times 7 times z. So part of the tricky part sometimes is finding that common factor when it's not immediately obvious. In this particular problem, we're pulling the 7 out, and then you multiply y plus 2 plus 3z to that 7. Again, this is the opposite of what we did at the beginning of the video. So let's jump right back to the whiteboard and do some factoring examples. Okay, so we're here back at the whiteboard. Let's do some factoring examples. Let's try 5y plus 20. So we need to find a common factor between these two items. What is something that is multiplied to get both of these? In this case, it's the 5. So if we divide both of those by 5, because we're going backwards, instead of multiplying with distribution, we are dividing when we factor. Let's pull a 5 out of both of those. So 5 times y gives us 5y. So 5 times what gets us 20? In this case, it would be 4. So if we were to go back to the beginning of the video, we would distribute 5 times y, and 5 times 4 is 20. So all we're doing is going back and forth, back and forth. Going this way is factoring, and going this way is distributing. Let's get rid of those pesky arrows. Let's do another example of factoring. Very similar. We'll say 9a plus 27b plus 18. Now, does anything stand out here? Let's fix that b. Does anything stand out here that looks like a common factor to all three of these? In this case, it would be the 9. So I'm going to pull the 9 out. I'm going to factor the 9 out of these three things. So it's 9 times three different things. In this case, first one is a, because 9 times a is 9a. So 9 times what gets us 27b? In this case, it's 3b. Now 9 times what gives us 18? It's 2. So again, going from here to here is factoring, and going from here to here is distributing, forwards and backwards. It's the same idea. They apply both ways. Let's do one more factoring example. What's a good one here? Let's say x, y, plus 3x minus 4x. So what is the common factor between all three of these items? In this case, we're going to pull out the x. There's an x here, there's an x there, there's an x there. So how do we get to x times y? Well, just be y. Here would be 3, and this would be 4. In this case, you could simplify even further. Y, 3 minus 4 minus 1. That's not necessary, but you see how we factored out the x. The last thing I want to cover in this video is the concept of like terms. So terms, such as 5x and 4x, whose variable factors are exactly the same, are called like terms. Terms such as 4y and 5y squared are not like terms. The variable has a different exponent, so they're not like terms. It's very important to understand that you cannot combine terms that are not like, that are not the same. So you can't combine 4y and 5y. Let's take an example of 3x plus 4x. If we were to factor this and pull out the x and say 3 plus 4x, it'd be 7x, or just 7x. So when you combine like terms, you end up kind of cutting out the middleman. 3x and 4x are like terms, so they can be combined, and you can skip right ahead to the answer, which is 7x. Here's a different example, 5x squared plus x squared. Now I'm just going to rewrite it here as 5x squared plus 1x squared. We're going to factor out the x squared because it's a common factor between those two items. So 5 plus 1 in parentheses times x squared. So this is the same as 6x squared. So when you combine like terms, you could skip those two middle steps. If you see 5x squared plus x squared, that's 6x squared. So that's a combining of like terms. We're going to go right back to the whiteboard and combine some terms that are like. Okay, we're back at the whiteboard, so let's combine some like terms. Let's start with something fairly straightforward. 9a plus 10a. So we have a common factor here. I'm just going to factor that out. 9 plus 10a. A is the common factor. I've pulled it out. We can simplify to 19a, and we would probably just write this as 19a. So in this case, we have like terms, and we can just combine them, 9a, 10a to 19a. And this middle part, we will end up skipping once we know we can combine like terms. So let's do this one. Let's do 2x plus 9z plus 6x. So which terms are like? Which is a weird way of saying it. So we've got a 2x, a 9z, and a 6x. So in this case, these have like terms. So I'm just going to rewrite it. 2x plus 6x plus 9z. Now I've got common factors next to each other. I'm just going to factor out this x. So we have 2 plus 6 times x plus this 9z all by himself. Simplify to 8x plus 9z. So again, this middle part will end up skipping. So let's do a skipping step. Let's try. We got enough room? We got enough room. 4x plus 5y plus 6x plus 2y. Now we know that when we add stuff, we could rewrite this if we wanted to. So just for the sake of this example, I'm going to rewrite this as 4x plus 6x plus 5y plus 2y. So what I've done is kind of rearrange so the x's are over here and the y's are over here. So instead of factoring out all the numbers, we can combine like terms and skip this step. We have 4x and 6x. That is 10x. We have 5y and 2y. That ends up being 7y. So we've gone from here to here without having to do all the factoring steps. We've got a weird one here. Let's just, I want to do this quick example over here. 1/2 b plus 1/2 b. So you got half a b and half a b. So you can just look at this and say, well, if I've got a half a b and half a b, that's a b. But let's do a little bit of math here and just kind of prove that that makes sense. We could combine like terms, just as we did here, 1/2 b, 1/2 b, and say we have, 2 halves of b, which is really b. But I want to factor this out. I just want to show that this still works even with something like a fraction. So in this case, I'm going to factor out the b and say 1/2 plus 1/2 b is equal to 2 over 2 times b, which is equal to 1b, which is equal to b down here in the corner. B, so it works. And that's it for today. If you feel comfortable with the material, we'll see you next time. Otherwise, stick around. We're going to jump over to some whiteboard exercises and cover everything that we've discussed today. Okay, welcome back to the whiteboard. We're going to go back to the distributive property, and I'm just going to write it up here. A times b plus c equals a b plus a c. So we're just going to keep that up there for the time being. So let's distribute some stuff. 6 times 5x plus 2. We've got a thing on the outside, 2 things on the inside. Give you a chance to look at this. So 6 times 5 times x is 30x plus 6 times 2, which is 12. We've distributed the 6 across the contents inside the parentheses. Let's do something a little more complicated, but not too much. I'm sure we can handle it. 4 times 3x minus 8 plus 2y. You just need to distribute the 4 across every item inside the parentheses. 4 times 3 times x is 12x. 4 times minus 8, so minus 32. 4 times 2 times y plus 8y. So we're just distributing the 4 amongst the items within the parentheses. Ready to go backwards? Just going to separate all of this. We're going to go backwards. We will now factor. We'll do the opposite operation of what we just did. So let's try 5x plus 10 plus 15y. So what is the common factor? When you need to factor and do the opposite, you need to find what can be pulled out of each item here. So in this case, it's 5. So let's divide each of these by 5 and see what happens. I'm going to put a 5 out front, start the parentheses. So 5 times what gives you 5x? In this case, it's x. 5 times what gets you 10? Well, that's 2. 5 times what gives you 15y? 3y. So we've factored out 5 to give us this. Again, it's the opposite of distributing is factoring. Let's do one more factoring problem. 4 14y minus 7x plus 21. Let's leave it like that. This may look familiar. This is similar to a problem that we did during these slides. So what's common between these three entities? In this case, it's 7. So we're going to take the 7, put it out front. 7 times what gets you 14y? In this case, it's 2y. 17 times what will give you negative 7x? In this case, it's minus x. And 7 times what gets you 21? That's 3. I want to do one more factoring problem where we're factoring out a variable. So we're going to put this up here and say 7x squared plus x minus 2x. Now this may look a little complicated, but what is a common factor in all of these? It may be easier to think of this 7x squared as 7 times x times x. So the common factor here is x. So let's just pull out the x. So if you take 7x squared and you pulled an x out of it, what would you be left with? It would be 7x. If you think about it, 7 times x is 7x squared. What happens when you divide? Oh no! Come here, eraser. How do you get x divided by x? Well, in this case, it's just 1. X times what gives you minus 2x? Minus 2. So you could simplify this. 1 minus 2, x times 7x minus 1. Let's jump over to like terms. And what I want to do, we'll just kind of separate this. I want to take this problem and look at it right now. Where are there like terms here that we could have combined? Now, as we said before, exponents, if they are different, they are not like terms. But in this case, x and 2x are like terms. We could have simplified this before we factored out an x and made this a negative x. So x minus 2x is just x. We would have skipped this middle step and not had this here. But let's look at some other like term problems. Let's say 7x plus 6y squared plus 9y squared. So which like terms can be combined here? X and y, they want nothing to do with each other. But we've got a y squared and a y squared. In this case, these are like terms. So we'll do the factoring example, but then we'll start skipping steps. So we'll write 7x, because he's lonely over here, plus, and we'll factor out the common factor, which is the y squared. Y squared. 6 plus 9, lonely 7x, y squared, 15, and then we'll just rewrite this as 7x plus 15y squared. And if you looked ahead, 6y squared plus 9y squared is 15y squared. So you can combine terms this way and not have to do this step. So this will be the last time that we bother showing the factoring, kind of proving the like terms idea. So let's combine some like terms without having to do all this extra math. Let's do 4x plus 3y minus z plus 2y. So we've got 4 components here. Do any of them share a like term? So we've got x and y, nope. Y's and z's, nope. So we've got a y and a y. Okay. So we got 3y and 2y. Well, how many y's is that? That would be 5 y's. So 4x plus 5 y minus z. That's all we can do with this problem. There's no other like terms that we can combine. Okay, let's do a challenge problem here for like terms. I'm going to say 2y plus 1/4 y plus y. So we all have the same variable. We all have the same exponent. So we could just kind of add this together. 2 and 1/4 and there's kind of an imaginary 1 here, right? And 1y. So let's factor out a y. Let's just see what happens. I'm going to pull the y out, even though I just said we weren't going to do that anymore. But with this one, let's just see what happens. 2 plus 1/4 plus 1. So I've factored out a y. So we could add this up, but let's find a common denominator. And I'm running out of room. Oh no. So I'm going to actually rewrite 2. How would I rewrite a 2 with a 4 on the bottom? So I'm going to just squeak this guy out of here. I'm going to rewrite this as 8/4. Right? 8/4 is 2. Just leave the 1/4 alone. How do we rewrite the 1 with a 4 on the bottom? As we learned a couple sections ago, anything over itself is 1. I'm just going to rewrite this as 4/4. So now I could add all this together. A plus 1 plus 1. It's 13/4. That's a terrible fraction. So this is 13/4 y. In this case, it was easier, at least in my mind, to factor out the y, do all your crazy fraction fun, and then put it all back together. That's it for today. We'll see you next time.